To start off this video, I first want to introduce a vocab term that is pretty common when talking about equilibrium, and that's the concept of dynamic equilibrium. Now, without you knowing, we've talked about dynamic equilibrium so far, especially with the milk jug demo. It's simply the idea that the two students that were pouring the water back and forth, we could have had them up there for the remainder of the period, and there still wouldn't appear to be a net change in the overall water level in those two milk cartons. And that's the concept of dynamic equilibrium, the idea that the system looks like it has stopped. However, it is working pretty hard actually to maintain that equilibrium. And also what that means is if it's ever stressed in any way, meaning you add or remove a product or reactant from the system, the idea that it's still working pretty much implies that the system can fix itself if it ever gets thrown out of equilibrium. And there was a French chemist named Le Chatelier that first summarized this behavior of systems at equilibrium and eventually developed a way to predict which way a reaction will shift in order to fix itself should its equilibrium ever be disturbed. So basically, how we're going to disturb a reaction is we're going to cause a change in the rates of the forward or reverse reaction. Okay, so by definition, in order to disturb equilibrium, we have to change the rate. The rates at equilibrium are constant, forward and reverse, and whatever we're going to do to the system somehow is changing the rate of the forward or reverse reaction. Now what the system will then do is develop a new point of equilibrium. The system's going to develop a new point of equilibrium. It's not going to change its equilibrium constant, but because you've added something or taken something away, there's going to be a new balance point or a new equilibrium point that must be met or reached in order to fix the system and maintain or reestablish equilibrium. Your answers to these questions on Le Chatelier's principle is simply going to be shift to the right, shift to the left, or some things don't cause a shift in equilibrium at all. And those are actually the trick questions that we want to be on the lookout for, and that slide is coming a little bit later. So once again, we get this idea of calling a system right or the products or left for the reactants, and the system will literally shift in order to maintain that balance. Let's take a look at the first thing we can do to disturb equilibrium. The first and probably easiest disturbance to equilibrium that is easiest to predict is going to be to add or remove a reactant and to add or remove a product. And what will happen in this case is if we, let's say, I like to think of this as an actual teeter-totter, where we've got reactants on this side and products on this side, and we have established some sort of equilibrium. I drew the two objects as equal there. They don't necessarily have to be, because we saw again with the milk jug demo that they can be different amounts of reactants or products. The point is we are balanced right now. However, should we introduce more product, all of a sudden this teeter-totter is going to want to not stay straight, but it's going to want to obviously shift where there is more stuff. So that is the disturbance to equilibrium, the fact that we're no longer in equilibrium. What this reaction is going to do is it's going to kick the reverse reaction in high gear and move some of this material to the left. So what we're going to do is reestablish equilibrium by moving some material to the reactant side should we add products. And what we get there is a new equilibrium point signified by the different amounts of material here versus here. Now, the same is true if we add a reactant. Now, if we add a reactant, we've got too many reactants, the reaction is going to shift right to reestablish a balance point. There are certain ways that we can remove reactants or products, usually by adding some chemical to the system that binds a certain reactant or product, or if we're producing, let's say, ammonia, for example, which is a common industrial process, the ammonia can be siphoned off, so product is constantly being removed. Same deal, if we remove a product, we're going to realize that there's too few products there and it's going to shift to the right to make more products. Opposite is true. If we remove a reactant, the system is going to realize there are too few reactants and it's going to shift to the left to make more of them. Another way to affect equilibrium is to increase or decrease the volume of a gaseous system. And that is so important that we understand that affecting the volume of an aqueous solution system is going to do nothing for changing the point of equilibrium. But if we do that to a gaseous system, we have to go back and remember one of our basic gas laws, and that is that pressure and volume are inversely related. So if we were to decrease the volume, let's say, on a system, we are going to increase the pressure. And most notably, we're going to increase the partial pressures of the species in solution, or I'm sorry, in the reaction. Now what that does for equilibrium then is you can think of decreasing the volume. You're giving the system less space to occupy. So the system is going to shift to the side of the reaction that has less molecules. Okay, so when we increase the pressure by decreasing volume, you're crowding the system. Therefore, it's going to shift to the side that occupies less space. So if we count, there are 2 gas molecules on the product half of this reaction, whereas there are 3, 1 here and the 2 here, on the reactant half. Well, the product half here, because it has 1 less mole of gas, is going to occupy less space. So since you're decreasing the volume and you're crowding the system, it's going to shift to the side where it has less molecules present, so that it does not feel as crowded. The opposite is true if you increase the volume. You're going to give it more space to roam around. The reaction will shift to the side with more moles of gas, and in this case that would be the left side. Another way is to change the temperature of the system. So as we know now that every chemical process is either endothermic or exothermic, and what you're going to see in these reactions now for these equilibrium expressions is you're going to see the word heat or an actual amount of kilojoules of heat added to either the reactant or the product side. And we can think of this as a reactant or a product. And in fact, we're going to solve these particular problems, these changes in temperature, exactly as we would adding or removing a product or reactant. So the ways you can be told where heat goes is you can actually have it written in the equation for you. The author of a problem will actually write the word heat into the equation. Or the problem will tell you that it is an exothermic reaction or an endothermic reaction. If it's exothermic, heat is a product. If it's endothermic, heat is a reactant. And as I said earlier, we're going to treat these things exactly like reactants or products. So in this case, when we've got this equation down here, we ask, is it endothermic or exothermic? And that's purely for review. Heat is over here, so this is an exothermic reaction. But if we remove heat, we can think of this as a product being removed. So we have too few products at this point, and the reaction is going to shift this way. Another way for them to tell you also that heat is being removed is to cool the reaction down. If they want to add heat, they might say they heat the reaction up. So be on the lookout for those key words. Okay, a few ways we can run into some trouble on Le Chatelier's principle. The first thing is, I guarantee we are going to be asked about adding or removing something that is not in the equilibrium expression. Something can only affect equilibrium if it's in the equilibrium expression. So if a solid is said to be added or removed, they want you to get tricked in that they're going to see that this is removed, it's removing a reactant or a product, and they want you to tell them that there's a shift in equilibrium. But remember, solids and liquids are not in the equilibrium expression, and then by definition cannot affect the equilibrium point. So if we have more calcium oxide added, we've got to realize that that's a solid, and we want to say no shift in equilibrium. Changing the amount of a solid or a liquid will not change the equilibrium point. The second no shift answer comes from increasing the pressure by adding an inert gas, and it's usually going to be a noble gas. So they're going to say 2 moles of helium were added to the system. Well, where you can get confused on this is it sounds like, well, before when we decrease the volume, we are actually increasing the pressure. However, when we increase the pressure by adding another gas, we have to remember the law of partial pressures, in that total pressure equals the sum of all the pressures of the other gases. So let's say we add helium to a system. all we're doing is increasing the partial pressure of helium. Now, the total pressure is going to reflect that, but you are keeping the partial pressures of the equilibrium gases the same. So whenever pressure is increased, fight the urge to answer the question as if the volume was being decreased and the pressure was being increased a few slides back. If we're adding an inert gas, there is no change to equilibrium because the partial pressures of the equilibrium gas are staying the same. It's just the partial pressure of helium that's being increased, and obviously then that's going to increase the total pressure as well. Finally here, we need to see the effects of catalyst on equilibrium. We talked last chapter how catalysts will lower the activation energy right here. So if we ever get asked in a Le Chatelier's principle question, what happens if a catalyst is added, we are going to answer no shift, because catalysts do not alter the equilibrium position. They will simply increase how quickly we get to equilibrium. So whenever we're asked about a catalyst in Le Chatelier's principle, we will not answer left or right. It's going to be no shift. We will get to equilibrium faster, but that's not what they're asking in the question. There's not going to be a shift. While we get to equilibrium quicker because of the catalyst, there is no shift.